This material has been reproduced and communicated to you by or on behalf of the Australian National University in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
All right, hello everyone. Welcome to week 4. So this is going to be my last lecture for this course. And from week 5, Professor Qin Wang going to take over. So I'll be on parent leave. So this week, we are looking into this entity relationship model. So this is a kind of different model to model the data relations. And then we will talk about briefly the relational data model and then this ER model. So we will use short notation ER model in this course. So there is a figure here. Anybody know what is this figure about? Anybody? This diagram, right? So we have a city. This is one of the cities in Germany. I think right now it become Russia, or it's in older times. And there are 7 bridges. There was a person who was visiting this city and found there were 7 bridges. And then he came up with a question, asked himself or his friend, together with the trip, and they were wondering, is it possible to just have one unique path, one path passing through all the bridges without repeating any of the bridges? So using this diagram to try to understand this problem. And then later on, a mathematician called Euler in the 1800s, I think is 1700, like about 300 years ago. Euler figured out this problem using a diagram. And the answer was that it's impossible to pass through all the bridges without repeating some bridges. So that was the answer. And then, so if you're thinking about that, at that time, maybe when they kind of having a trip in the city, then they need to try to understand, right? Try to understand and how to consider this problem. So basically, the mathematicians used idea to do some abstract work in a diagram to show all the bridges, and they consider the connections. So this diagram has helped, for example, the mathematician Euler to figure out the problem. So in our case, we have also a very complicated scenario where we have all the data from different kind of angles, perspectives for one task, right? We have then a diagram may help us to understand the relationships between all these different pieces of the data. So ER model is all about diagrams. How can we understand? How can we use a diagram to understand the data? And then we use this kind of thing as a model. So different angle of using a diagram to do modeling. So this is week 4. And now we have assignments and lots of labs, and then each of us may have many courses, so it's kind of quite busy week, and it can be very stressful. So I would like to say that do take care of yourself. There's lots of business or stressful moments in these weeks, right? From, lots of courses, assignments, and deadlines. So do take care of yourself and keep always a positive perspective of life. Be happy. At the end of the day, this is just a course, right? You have a life to live on, and then just be happy and be healthy. Keep that in mind. There will always be challenges, and then there are also supports from the university. So we can search for all these supports from the university and just try to face these challenges. Like we have this SQL type of coding or these things. They sometimes can be very stressful, right? When we're debugging a code, it maybe takes a few days or a few nights to figure it out. I've been through these moments, so I do feel the kind of these similar things. And then there are many new topics, new concepts for this course. So and then sometimes when we look into a particular topic and then we forgot about the previous concept or terminologies, and it's harder to keep track of all these terminologies at the same time. So it can be stressful sometimes. So do take care of yourself and also your colleagues or friends or neighbors, right? And then we have these assignments which I published last Thursday, and I posted on the WhatsApp page. So make sure that you start early for this assignment. So this is more about coding, and then be sure to check the deadline. So the deadline is going to be the week 6 on Friday, 5 p.m. So be sure that you get it submitted, and you can submit as many times as you want. So you can start to submit like whatever, like if you figure out already 6 programs already, you just submit it and then try to keep updated. So keep submitting all your newest or the latest version of your assignments. So no extension will be given for this assignment, and then got to be remembered that this work has to be individual, no group work. So no group work. Ask and read the questions on WhatsApp, but do not post the solutions. Don't post solutions or hints there. If you have some confusions with particular programs, then post that in the WhatsApp page, but try to not disclose the solutions. So your queries must be dependent on any specific database state. So we are kind of asking the coding, the code that you will send a piece of code, and then try to use comments to tell us what's your reasoning, what's your logic when you come up with these particular sentences. Because those are going to be very helpful in the case that if you had a wrong answer, but then you will get some partial credits for these kind of questions. So those comments are very important, so to keep that in mind. And then when you submit your .sql file, put the comments there. Okay. Partial marks, yeah, as Ariel said, that will be awarded. So be sure to explain each of the query in the SQL file you submitted. Any questions about assignments and quick questions? Okay, if not, let's go to the next one. So a little bit to review now. So what did we learn this week? So roughly we had 4 videos. 2 of them are like about over 23 minutes. The other 2 are like 12 or 13 minutes. So what about a total 40 plus 20, right? About an hour or hour and a half. Materials there, so look into quite some parts which towards why we are going to do this data conceptual design, this ER model, and how can we do that, right? So a little bit of motivation is that why we started this database conceptual design. So at the end of the day is that we want to reach a certain goal. In particular, that there are many software projects has tendency to fail. And then we want to use this model to help us to develop software project which can be more successful, or successful rate can be much higher. So a good design phase will have a lot, but no guarantees. Still, there are many different aspects that can fail a particular software project, right? So this is just trying to kind of increase the chances to have a successful software project. So this kind of design is kind of useful, like in the future years, if you have a startup company, right, then you can consider these kind of concepts or these kind of tools that you may look into, which give you a much successful startup case. So this week we look at this conceptual design. In particular, we look into the entity relation diagrams, and then there's an enhanced version, enhanced ER. These enhanced ER models are the cases where we have to consider the subclasses and the superclasses cases where basically the goal is bigger, right? Why is this even relevant, right? So there are many real-life kind of projects. For example, these Victorian hospitals use all these SQR codes coming from kind of ER models. They start with some ER models and then later on map it to some data relation schemas, right? Similarly, like the Melbourne startup companies, or even like as I just mentioned, that if you start your own ones, maybe you wanted to look into something like this, right? Some other real-life programs. So from ER design to this databases logic design, so at the end we go to the databases schema. So ER diagrams attempts to capture the requirements of the databases project. So we are given some tasks, and there are some specific requirements and then goals that we want to reach into. So these ER diagrams help us to understand what is going on, right? Just like the 7 bridges program, this diagram help us to identify what is going on somehow mathematically. So we are building models on the real world, right? So relate what you do to your understanding of the real world, just like the 7 bridge programs as well, or you have some other programs, maybe you want to draw some lines in your paper and then try to understand this better. Even there were some other stories, right? For example, in the early time, like when people do the translations, right, the translators, usually they have a piece of words, connected them somehow, and then they can do the simultaneous translation when a politician speaks in public, or some other cases where they need like simultaneous translator. And then those translators, they have their paper and they write all these simple words and then connect them and then build kind of this kind of relationship as well. So this kind of diagram help a lot, and then somehow it's built the models from the real world programs. So we are modeling in particular data, right? So entities and the attributes, and then all the relationships between these entities. And then the relationship can also have attributes, because relationships can have different properties. So we are identifying, for example, also how to uniquely identify entities, or like, for example, the keys, candidate keys, or primary keys, right? Restrictions on relationships. So the relationships has like 1-to-1 binary relationships, 1-to-m, and then many-to-many. So here n just means that we have many-to-many possible relationships. Once we have our conceptual design, we want to convert it to a logical design. So this course is this lecture is about conceptual design. And then logical design is, we are mapping the conceptual design to logic design. And then logic design is what we have already mentioned about in the first 3 weeks, and that is the relational databases or the tables on this relational schema. Now, how do we construct a ER model or EER model? So EER stands for the enhanced ER model, entity relationship model. So putting in a kind of informal process, these are the steps that represent any business requirement. We have roughly these 7 steps. First, we want to identify what's the entity types, including the weak entity types. Like what are the major bodies under this kind of the business. And then we also want to identify the relationship between all these entities. And then each of these entity type and relation type, there are attributes. Right? And then we want to identify all these ones. And the attributes always have these domain constraints. So you also want to consider what is the domain of these attributes, both for the entity and the relationship. So both of them have different domains and constraints. So identify a primary key for each entity type. And then classify each binary relationship from the step 2, right? And then the 6th step is determine the partition constraints of each entity, each of these binary relationships, or some like one-to-many relationships. Determine the disjointness and the completeness constraints for each of these particular case where we have the enhanced model. So this last line is for the enhanced ER model, where we have the subclasses or superclasses. Now, you may take a little bit further look at this 4th item here, identify primary key for each entity type. Why we did not mention about if we want to identify a primary key for the relationship types, right? So like the first 2 steps, we want to identify these two parts, right? So why is that we don't specify that we want to identify a primary key for the relationship data? Any thoughts? Why is that? Each relationship has its own attributes, as well, right? And then maybe there can be some tables, right? And then this table, usually we want to identify some unique attributes which can be used as a primary key, right? So the major reason here is that for a relationship type, because relationship is always between at least 2 pieces, 2 entities. So these are always associated with another entity at least, right? So when we define the attributes for, if we convert it to a relational schema, a table, then when we define the relationship schema, we always need to pick some sort of the primary key from one of the entities to uniquely identify this table. That's why like this relationship data type, or once you get a table, this will be associated with a primary key from one of the entity type. So somehow that primary key is identified through this entity type. Does that make sense? The difference, that's the major difference here. Now, those are the symbols to represent items in diagram, right? So now we think about it. Like suppose that, say, maybe 50 years ago, because this was developed like about 50 years ago. Say if it's 60 years ago, right? Then 60 years ago, when we talk about this kind of things, what can we do? And then people have to maybe join some papers and then to think about how to represent pieces. And then these are somehow unique set of symbols to represent this kind of relationships or these entity relationships in a way that they have already thought through about this process. What are the good, why we choose some circles or diamonds, rectangles for representing particular things. There was some work has been done there, right? But then if 60 years ago, if you are the person to design such a thing, maybe you come up with something different to represent different things, right? So this is kind of just a set of convenient symbols, just like mathematical symbols, right? In the water page, we had some questions asking about like mathematical symbol where we have an element that belongs to a set. Why we are using this symbol like that one, like the E, which are facing like with curved lines there. Why the symbol is like that, right? So there was some stories behind it, right? For why the mathematician came up with that symbol. And then if you think about other symbols, right? Maybe you have already taken some calculus courses. So calculus, if you think about this integration sign, the integration sign is like a S, where S is like elongated, right? It's a longer S. And S short for summation, actually. Summation. So you take the S from the summation, the word summation, S, and then you put it longer and you get the S. Where that S is become an integration sign, the symbol for integration, right? And then now it becomes standard for whole mathematics. But then that's kind of the story behind it. Similarly here, so there are so many symbols. And then those symbols, for example, the entity using a rectangular box, probably this one, why, if you think about the logic behind, to me, it's because this symbol is probably the easiest one to draw. And then the entity is mostly often used the things that in this relationship we want to describe. So entity, weak entity, well, the motivation of understanding why the symbol represents each thing is, the motivation is that this may help you to memorize, right, what symbol means what. So that's why I spent a bit of time to talk about this reason behind it. Like this diamond relationship, right? Why we use that one? Because maybe there are two angles here which we connect pieces of information, right? And then identifying relationship. So these are like for this weak entity and this identifying relationships, those are for subclasses, right? If you have an employer or employee, maybe the employee has a child, and then that becomes a subclass. And in this case, then we use weak entities and also identifying relationships, those kind of logic behind it, right? And why we use these double rectangles here for weak entities, right? Because in general, weak entities, because you have to draw more information, more lines. It's basically taking more time to draw those ones, right? The reason behind it is that those ones will take more time, but this will appear less often in general, in a real scenario. All right, so some other ones like attributes, using this one for attributes and the multivariate attribute. And if there is a key attribute, or a primary key in this case, the key attribute will be using underline. And then in a subclass is partial key attribute, so dashed line. And then total and partial, this is for participation constraints. Say one lecturer, maybe it's in a department teaching some courses. Those like if it's partial or it is like total. Like for example, this course I'm just teaching partially, right? Professor Wang will be teaching the other part. So this is like a partial. The partial one is in default, and total is specified, the case. So ISA, so ISA is for the purpose to identify these subclasses. Okay, so those are the symbols that maybe we want to memorize a bit. And then there's another case where we have a disjoint or different relationship or overlapping relationships between the subclasses. And then now that's give us some general philosophy to get a ER diagram. And then once we have this ER diagram, we want to convert it to some relational data schemas. So this is kind of an algorithm, or say steps or procedure to convert an ER diagram to relational schemas. So those are 7 steps, and then you may question it, right? Because we have this step 8. So step 8 is here in the sense that in the case that we have subclasses or superclasses, because sometimes these subclasses or superclasses is not needed in your ER relationship diagram. So those major 7 steps is basically mapping the regular entity types. Mapping, once you have a rectangle, maybe you want to map it to a table, a relational schema, right? That's first step. And those ones are the easiest ones because you have a box, and then the box has some lines connected to all the ellipses, and then you can define all this schema of the tables. Mapping the weak entity types, so those are for the cases where have the double boxes, right? Rectangles, I mean. So mapping the binary one-to-one relationship types, so there are 3 approaches. So foreign key approach, merged relation approach, and cross-reference approach. All these three approaches are slightly for different kind of goal. Particular is the participation scenario where you have the total participation or partial participation. Say the foreign key is for one-to-one partial relation case, participation case. Well, other ones like this one, cross-reference approach is for the total partitions as well. So anyway, these are the 3 cases for mapping some relationship to some table. We will go to more details in a second. So step 4, mapping the binary relationship, 1 to n relationship type, and then mapping the other ones like many-to-many participation case. So step 6, mapping the multi-valued attributes. That's in a relationship that we have this double ellipse that can happen with multi-valued attributes, and then we are talking about that, how can we build up that mapping. And then 7 is this n-ary relationship types. So that's the kind of the whole procedure, right? So where we start with some requirements for a goal for some business or some tasks. And then we kind of first collect these requirements, do some analysis, think about it. And then the conceptual design, which is the diagrams, ER relationship model in this case is more formally, so more formal in this case because we have more well-developed set of knowledges. That's why we look in like this conceptual design. And then the logic design is to map it to relational schemas, where putting into SQL scenario, you can just, then once you have these tables, you can look into the information to the query on the tables. And then physical design, which is the database system management. This lecture is focusing on this conceptual design. So it is a process of constructing a conceptual model that is modeled as a high-level abstraction, like we're using these symbols, sufficiently simple and often graphical. So graphical using these diagrams, use the communicated to requirement databases or non-technical users, right? Or if you are a boss, if you are the CEO of the company, maybe you want to talk with some other people, CEOs, and then what's the structure of your company? How do you manage your databases? Can other people trust you, right? And then you try to convince them, maybe you have to think about a way to convince them easily, because everybody is very busy these days. So those are like for communication as well. So it's good to have this set of tools, right? So a conceptual data model is built using information in user's requirement specification. Right? So the conceptual design is based on ER model in this course. There are other models, by the way, so you can look into that. So talking about model, so what is model? Right, what is model? So in the very first slide, we showed a diagram for the 7 bridges. That's our model. That's a conceptual model. And then you can analyze them mathematically. And then you think about other things, like all the greatest scientists, what are they doing? They are all basically building models. For example, Newton, right? Newton's second law. Newton's second law tells us that the force equals the mass multiplied the acceleration. That's our model. That's a mathematical model to model the real-life world problems. An object or a car is moving in the road. There's an acceleration, there's a force, and then there's all this, the mass of that object, or the velocity, distance, how much distance this car traveled. These are models, right? So a model, in general, is a simplification of reality. Often, in this case, we use graphical description of this data, because we are focusing on data right now. And then associated with a modeling language. So in this case, like SQL language. And then in physics, right? Physics, then people look into a different way of doing the modeling. Say like computational fluid dynamics, they look into how the fluid travels. Like usually model it as like differential equations, right? If you talk about like like Albert Einstein, he somehow is just a modeler in some sense. Because he model like how the universe works. Like the gravity, you have this large mass, like sun, with a large weight, right, on some sort of surface, and it distort the space-time. That's kind of a model. And then this model somehow is a more accurate model to describe the universe than the previous ones, like from Newton, where look into just the simple force equals mass times the acceleration. So at the end, the different models have different advantages or disadvantages, have the pros and cons, right? So there are many, many models. And then what does the model do, right? So modeling is kind of process from something to reach something. So it creates understanding and relationship of components of the system, helps in the conceptualizing and visualizing the structure of the system that we may want to build. Right? Facilitating the specifications of the behavior of our system, gave rise to the template, the guides, and the us in constructing a system. In particular, we are talking about this system of the data. So model comparison. So we talked a little bit about the relational data model in previous 2 weeks, roughly. And then now this week, we're looking at the ER model, right? You probably see this slide in the video as well. So this comparison is very useful. I always want to maybe like try to memorize somehow in a picture sense that what are the pieces connected, right? When I was talking about the relational schema, I also had this comparison between the relational schema with the tables, right? The usual Excel tables, and then we had that comparison. So we think about it, what is going on here. So you have a table, you have relational schema, Now we're talking about the relational data model comparing with this ER model. So this abstract level is changing. Table, relational schema, and then this one is more like conceptual. So this is the process, right? Remember the very first lecture I always talked about that, that's procedure, right? We have the data, you go to information, go to the knowledge, and then go to wisdom, right? That's the ultimate goal. Now, I hope you can see a little bit the sense what's going on here. Table, relational schema, and then this more conceptual case, which is this diagram, ER diagram, more abstract in some sense. All right, so this comparison, basically each of these models has attribute, domain, and the super key on this important information. The tuples, let's look into the entity relationships. The details and the relation is a entity set or relationship set. Relational schema at the end, the whole table, or it becomes the entity type, relationship type. Okay, so that's the model comparison. I want to kind of repeat this slide here just to emphasize that this importance or the level of kind of study the process, right? Or connect to week 1 lecture. So I want to build that connection, and then so that you can appreciate what is going on here. Okay, so in ER model, so again, those are the cases where how can we represent attributes as oval or ellipse. Sometimes I call it ellipse as well. Key attributes with underline inside this attribute, entity as rectangles, and the relationship with diamonds. Now, let's do some examples, look into some particular examples. So basically, there are 4 phases, right? So this is phase 1. So this is, we collected the requirements. These are the requirements, say, I already collected. And then we can look at these requirements, the collected information. And then we want to, this is phase 1. Phase 1 is already done. And then now we go to the phase 2, which is doing the conceptual design. And then from here, we want to build a diagram to understand what is going on here. And then again, I really like the example of the translator, right? The translator, because the politician is talking lots of things, too many things, right? How can you translate efficiently? How writing fewer words, like less words or some symbols, and then when you repeat, you can still able to get the most of the information of what the politician said, maybe after 10 minutes. Then those are the challenging parts, right? And then that's what's going on here, right? Here we have so many words, and then we build a diagram, and then from diagram we can translate it back. Okay, so read this a little bit. So we consider the following data requirements for the university student databases. So this one somehow is familiar for us. That is used to keep track of the students' transcripts. So there are several items. The first one, the university keeps track of each student's name, student number, social security number, address, phone, birth dates. Both social security number and student number may have unique values for each student, right? So here, social security number definitely is a case from the United States, not here in Australia. But that's a kind of identification to identify this unique person. So in this case, right, once the students in the university has a uni ID, and the uni ID and the social security number can both be unique. And both of them can be candidate keys, and then you can pick one of them to be the primary key. Now the second one, each student has exactly one major, may have some minors, right? Minor within some departments, and then, well, this is just a case, right? Maybe some students, they do have double major. They want to have more, say, I had many friends who had majors in computer science, also mathematics, because those are all quite important. And by the way, and this guy who actually invented this ER diagram, he did his study in applied mathematics, actually. In mathematics. And then he also had some study in the computer science. And he came up with this whole set of things that nowadays we are learning from this guy, right? Peter Chen, he was at MIT at that time. Each department has its name, department code, office number, office phone, and colleague. Both name and code have unique values for each department, right? So those unique things can be used as primary keys. And then, again, like say in this case, that department can be an entity, right? And then the next one is that each course has a course name, description, course number of semester hours, and other information. Now, what is the things that can be unique? In this case, is the course number. And then the other part, each section of a course has a structure, semester, year, and the section number and the other informations about this section. And then finally, a grade record refers to each student, and a particular session consists of final mark and the letter grade. Like that's the whole goal which we look into the student's transcript data management. So this is a bit of analysis, right? Maybe at the very beginning you are giving a different paragraph or longer paragraph, and then those are already bulleted, and in each item, so say you can consider this as some sort of the analysis in the data. Now we want to identify what are the entities, what are the relationships and attributes, and then start to build this diagram. That's the goal. Now looking into entities. Entities are the things in the real world, maybe independently exist. So the things, like for example, those are basically in the language is just the subject, right? The subject of the sentences. Subject of the sentences are the entities in this case, or sometimes maybe in the other part of the articles. Well, a relationship, associations between the entities, talking about the two entities at least, and the attributes for each of entity and the relationship. Now in this case, each student has a name, a student number, social security number, so this is a copy of the sentence we just had previously. So in this case, the entity is student, right, student. And then relationship, there's no relationship because we are only talking about the student. There's no other information here yet, right? So no relationship in this case identified. And then the attributes is that what are all this information here, you just copied here. Now you have all these entities and then the attributes. We identified, right? What about the other sentences? Basically, we go through each sentence and identify all this information, so one by one. Now each student has exactly one major or may have some minor in some department. So in this case, the entity is student and the department, because the students and they within some department and take some courses. Now the relationship is that student has major between in some department, right, or minor in this department. And the attributes in this case, like the name for this major and then for this minor as well. So those are like example to identify the relationship. Now identify the entities and identify the relationship and the attributes at the same time, and then maybe you go a little bit further to identify the primary key as well. The other part is the cardinality ratios. Specify the maximum number of the relationship between an entity that can participate in a certain kind of relationship. And the participation constraints can be total or partial, like that's looking at the relationship. Specify whether the existence of entity depends on its being related to another entity through some sort of relationship. So those are constraints in relationship, right? Again, the relationship can be defined as a relational schema, and then we want to put some constraints there. And then this is constraints for ER model. Then in the relational databases model, the constraints are different, right? Somehow different, but they can translate it. Each student has exactly one major and then some minors. In this case, what are the constraints relationship between has a major with, right? So cardinality is that each student has at most one major. So this is just scenario, right? One major in this case, and a department may offer many majors, right? So that's the cardinalities. Cardinality of a sets. Maybe you think about the sets, right? And that's cardinality. And then the ratio is talking about the entity to entity case. So that's why we are saying that this ratio here. And then participation constraints, every student must have one major, so this is total requirement. And then each department typically have like at least one major, and this is also a kind of total participation constraints. But for the minors, it's a little bit different. For the minor is that the participation constraints, every student may or may not have one major, and minor, and then each department must typically offer one minor or more, right? That more. So there's a bit different when we're talking about different relationship type. Now go back to identify maybe other parts which we have this other sentence from that list with the relation. From the information we collected. So each course has a course name. Those are attributes. And attributes as well. So in this case, entity, course, department, and then relationship is that this department offers this course. Right? And similarly, those are you can identify the attributes. And if we think from another angle from the same sentence. We can look into a relationship type, which is offer. The department offer this course, or the course is offered within this department, right? So cardinality ratio, look into every course is offered by at most one department, and department offer many courses. That's the cardinality ratio. So whenever you think about cardinality, you always go back to your mathematical concepts in the week 1. Like the mathematical concept, cardinality of sets. Think about that way. And then participation constraints, every course must be offered by some department, or total may or may not offer some courses. So that's the kind of partial. So we want to identify those ones. Once we identify those kind of pieces, and then we put them into the diagram. Now there are other longer sentences, or at the end, we just go through each sentence and then try to identify what is going on. So in particular, I want to mention here is that there's a subclass case in this case. Because a course, for example, typically in the United States, if you go to a university, the university, say Department of Mathematics, they have a course which may be called calculus. Then calculus, this course may have different sections. And then because in the US system, it's a little bit different. Like in our course, we have 500 students, 550 students, right? But in the United States, if they have 500 students, they usually offer different sections. Even the same course name, they have section 1, 2, 3, 4, and then say 500 students may be divided to be 5 sessions. And then these 5 sessions are taught by 5 different professors. And then each professor just taking one course, and then that's a different structure. So in this case, this section is entity, but this entity is a little bit different. It's kind of, you have to first look into the course number, primary case in course number, and then go to your subclass, which is a section. It's like, you go to the course and then choose a section, just like the lab sessions you are in right now, right? So you can say, consider your lab sessions to be a subclass in this case. And then when you do query to locate some lab for some students, then you have to go to the course name first and then go to the lab. So we're talking about how was that translated later on. So this is a subclass, and then those are the classes. The original entities. Subclass you can consider as like a sub-entity. You can rename it as you want, right? To help you understand the thing we are talking about here. Relationship, so like the section taught by some section, maybe attributes, you can put in some attributes. These are between the entities or with the relationships. So attributes, for each section, there is a instructor, semester, year, and the section number, right? So this is a weak entity, Okay, so another way I usually think about this whole process is that I usually, if I do this work, I put a piece of paper beside where this piece of paper give you all the symbols. And then you have one piece of paper here describing all the requirements. You have another piece of paper here showing all the symbols. You can put these two papers and do the connections. Like you say, you have some box here, and then you connect maybe to the university, to the department, then you get an entity. Like some ways of maybe doing some assignments, right? You can do something like that. And they gradually just move around all these entities, the boxes, so they always change directly there. So constructing this EER and EER model. So again, EER is for the enhanced case where you have subclasses. So this is the procedures where you first identify the entities, identify the relationships. We have done that, and then they identify the attributes for each of these ones, right? Cardinality ratios and participation constraints on the relationships. At the end of the day, we end up with something like this. Now, for example, we take a look at this piece, right? Where, like, say, department, right? So the department is one entity. You have a box, and then there's a department code that has a bar there, has an underline. Underline means the primary key, meaning this department has a primary attribute. Primary key is the department code. There has other attribute with the department name and the office number, phone, and the college, right? All this information. Then you can later on convert it to some sort of table, right? And then the weak entity, this like the double rectangle, look into the dashed key, right? Dashed line to represent the key inside this section. Okay. That's the for this case. You can go through that piece of paper here, and then try to build your own ER diagram. So one thing I want to tell you is that this is not unique. This is not unique. Maybe different of people may come up with different diagram. So different translators maybe do different work, right? So it's not unique. The major goal is to capture as much information as possible. Okay. Any questions? So there's a software to draw the ER diagram. You can download and practice. So basically this software is just to help to draw, instead of draw these pieces in the paper. In a paper, you can just use in computer software program to do that. So you can try to draw the diagram from this software, TerraER. And then those are some informations that you can export into some figure or some different format as you want. You can export it into PDF as well. And then you can download this from here, in GitHub. And also you can double-click on, based on different systems. And also potentially you can just try to search around on the Google Internet these days. Then you just maybe use a different software to draw this diagram. Let me stop here a little bit, and then we take a bit break. And in the meantime, so we take about a 12 minutes break, so we come back here in 2:10. In 12 minutes, you can look into this access, this program, and then maybe you bring out a piece of paper, try to identify what are the entities, and then try to draw a diagram. And then we come back and talk about how this was transferred to some diagram. And then the second half of this lecture is mainly focused on how to convert this ER diagram to some relational schema. And then, yeah, we see you in about 11 minutes. Take a break. We come back in 10 minutes. All right. I hope you have done some access to get a diagram, roughly. Anybody want to share your results? Or maybe identify what are the entities and then some weak entities here for this case? Anybody want to share? What's the first entity you identified in this case? Shops, products, anything else? Customer, yes. So basically, you really look at the nouns, right? N-O-U-N, right? In these whole sentences, whole set of paragraphs, and then the subjects. All those can potentially become the entities. So in particular, here we identified all this kind of the entities in this case. Well, maybe like, for example, you may also want to consider, say, the company also is an entity, right? You can consider that as well, but that one is not very important here in this case. So the products, the company sell the products, that's kind of the main purpose, and then from the stores, which have the local shops, the physical shops, and then web stores, right? And then, so some other ones like web store, shops, so those are entities. And then once you identify an entity, maybe you want to consider also is it a weak entity or just a normal entity. You ask yourself this question, right? So in this case, when we look into the shops and the web stores, they are all stores. So stores is more like in a higher abstract level, And this high abstract level, it's more like the super class. And then this the physical shops or the web stores, they are considered to be the subclass. So those are weak entities. You consider like this way. So which one is more abstract, more higher level? Which one is more lower level somehow? And then other entities like a customer and or delivery. So first step, identify the entities. So shop, web store, product, customer, order, delivery. And then identify the subclasses in this case, like corresponding to the disjoint or completist constraints. So company sells products in both local shops, as I just mentioned, also on internet, web stores. So, and each order is associated with some shop and then web store. So you consider these subclasses as the shop and the web store, two different scenarios. And then the superclass, which is somehow higher abstract level, which is the store, and then consider what the disjoint or completeness is looking to what like the physical shop and web stores, they are disjoint, right? These are disjoint subsets. If you think a little bit mathematically, then the shop is a subset of the store. Web store is a subset of the store, right? And then disjoint, meaning that the intersection is empty. So you have two sets, the sets for the shop and the sets for the web store. You take the intersection, there's an empty set. That means disjoint. All right? Identify the relationship. So once you identify all the entities, you can check again what's going on and then to identify if I missed any important entities or not. Just take a check. Check the entities if they are correct. Now this one is to identify the relationships. The relationships is like, for example, in this case, a customer may place an order. So usually between two entities or many entities, a few entities, right? So custom is an entity, order is an entity, so the two entities connected by a relationship, which is a placed order. And then that consists, so now an order consists of some products, at least one product. So the order is connected with product by the relationship consists of. And each order is from either a shop or web store. So now, once you identify these entities, you look into the sentences. If in one sentence have like two entities in that sentence, once in that sentence, there must be a relationship type, relationship there. So similarly here, and then that's connected, right? Delivery method can be requested for each order, like this one, right? Okay. Now, maybe like if you look at the other sentence, like this sentence, right? Customer have 3 payment options, but not for each order, only 1 payment option, right? This one you have like customer and order, 2 entities here. Now maybe you identify another kind of relationship, but the relationship is actually already identified here, right? Please, so you don't need to do that twice. Okay, so those are the identified relationships. So customer place an order. Order consists of products. Order is from stores, and then delivery is on order. So and another thing is that when you think about this procedure, you're also thinking about you can step back and then does it make sense? You ask yourself once you have a relationship type, does it make sense? Right? Or do you miss a relationship? How you consider this thing? You consider by asking the person, like in real life, can this whole process have some bugs, like have some holes in the sense that if a customer can successfully get the product, and then what's the whole procedure, right? So you ask a question like this. So identify also the entity and the relationship, the primary keys, because each entity has a set of attributes. And then each of these entities try to identify a primary key. In this case, product, you can product ID using that as the primary key. Or customer, you have customer ID, you can identify that one as the primary key. Similarly, for the superclasses, store, or either location or a link, right? That's can be the information to identify the store. And then in the subclasses, now subclasses, you are not necessarily have a primary key, but you have a have a kind of weak key, or some information to identify the difference within that subclass. Within a physical shop, you have a shop number. Within the web store, you have a unique link. So, and then the relationship, and then once you have the relationship, then the constraints are looking at like participation constraints. For example, if it's a total, if it's partial, ask these questions. If it's one to many, or many to one, or many to many, this kind of constraints. And then similarly, you look into, as what I said, this is for the participation constraints. This is cardinality ratios. Look into the cardinality of the sets. So this is what I just mentioned about the participation. So now, very important thing is that not all the constraints. By the way, this process can be. There's no particular order. You can maybe, if you like, you can first identify the relationship and then identify the entity. You can do that in different order. There's no particular order. You can, at the end, we just want to get a diagram, right? And not all the constraints can be expressed in a diagram. There are some other informations that may not be able to expressed in the diagram, right? So for example, here, some information, for example, after full payment is received, a delivery would be sent out subject to product availability. And this information is not particularly talked about here, and then it cannot really captured in a diagram like this, right? So, for example, this is a store, right? This is an entity, right? This store has disjoint sets of like shops and web stores, and then the store has like a location or the URL for the attributes. And again, I mentioned that the subclass sometimes can be a weak entity, and in this case, it's not like a rectangle, double rectangles, because here they can uniquely identify as well, and it can be unique by itself, and not need to be really a weak entity here. Right? So you can basically, one of the sentences, if you are the translator, you look into one corner and then you are able to tell the information there, you can recover, translate back to the sentences. Now let's go to the next phase. So we have 4 phases. The next phase is to go into the relational data model from the conceptual model. So logical design, this is called. Logical design is the process of constructing a logical data model. In this case, it's a relation model. A conceptual data model is translated into a logical data model, which can be further refined or analyzed, right? And then, particularly, it is coming from like an ER model and then mapped to relations with primary or foreign keys in an SQL setting where we can do the coding. So the logical design is based on the relational data model in this course. Again, there are other models, right? So for this course, we use relational databases. So a little bit of recap on the data modeling, right? The requirements, we look into the requirement, a set of information we collected, and then draw a diagram to understand what's going on here. That's the conceptual level, and then go into the relational databases schema, the schemas, like you SQL, and create all these tables, all these schemas. And then the physical level is where we store and then manage these data sets. ER design is subjective, meaning that there are many ways to model a given task, given scenario, given goal. Analyze alternative schemas is important. Maybe some are more efficient, some are less efficient, depending on what we want. Constraints play an important role in designing good databases. Like what are the constraints we look into? Not all the constraints can be expressed in the ER model, like I just mentioned, that some information cannot be described in the ER model. Like even a translator, sometimes it's harder to translate. If there's a politician, said something like a poem, right? A poem, maybe a typical Chinese poem, then the translator, you translate it to English, and it's very, very hard to translate that poem to particular language, right? Or you lose many information, particularly the beauty of the poems, and they can be lost in that case. So it's not always like you can do that, express beautifully or efficiently. Well, not all the constraints in the ER model can be translated as just mentioned. A good database based design requires to further refine the relational database schema obtained through this ER diagram. So you can do this process, and then once you build up this relational databases, and maybe you do some queries, and you found that this query take a long time or a lot of storage, and maybe you can try to reorganize a little bit. Going back to the diagram, change how you convert that diagram to the tables, and then you get a different efficiency. Now, those are the steps that I previously mentioned, the 7 steps to convert an ER diagram to relationship. So again, step 1, so once we have an entity, which is a rectangular box, and then those are attributes, right? Now we want to create map this guy, this entity to some sort of schema. So for each regular entity type, E, create a relation schema with the attributes. So attributes are over in this case, right? And in this case, we first ignore the multi-valued attributes until step 6. Step 6 in particular, we will look into how can we create the schema, relational schema, if we have an attribute with multi-valuable values, attributes like. So in this case, right, we have this course, and then we can just go to the SQL library, and then we do create this course with the name, and then maybe we have the domain constraints, right? Domain constraints, course number, course name, all the attributes here, right? So remember that when you do the SQL coding, then you need to also specify the domain type, So this is not necessarily the final relational schema of the course in this case. So it's easy, right? Basically, once you see an entity, you try to make a table, create a schema, relation schema. Step 2, weak entity types, like these boxes, right? This section is a weak entity type. So for weak entity type, create a relation schema with the attributes plus the primary key identify the entity type. Now the primary key has to come from the superclass, which primary key is it's kind of partial key attributes inside this weak entity, plus the primary key identify entity type, which is in this case. So here, foreign key reference from the primary key to of its identify entity type. So here, this diamond has like double line as well, right? So you can see here that when we want to create a relational schema for the section, if you just using the section number in the whole databases, you may not be able to uniquely identify it, right? The section number is not enough. Only in the case that you consider the section number also the course number, then you can uniquely identify this. Like you are in a lab session, maybe you are taking another course, you are in a different lab session, and then this lab session has to be combined in the course number to uniquely identify this tuple, right? So in this case, for weak entity types, we usually needed to have 2 pieces of information, where inside this section, you have the section number and then the course number combined together. So now the primary key is section number and the course number. Now the course number in this relational schema has a following referential constraint, right? Referential constraint from a different schema. The different schema is the course schema. The course schema is the course number. And then those foreign key constraints is on the primary key in this case, right? Now step 3, so we're looking to the relational types and the barrier relations, and we have like 3 different ways of doing this. So the first one is that for a 1-to-1 relationship with type R with one total participation. So you say this side is total participation, double 9. This is partial participation, right? Partial participation. And then in this case, if we have total participation and then the partial participation, we always go from the total side of entity type. Total side, which is the double 9. Now you see here, double 9 from like from this side, double 9. Like say you can consider that double 9 has more weights, and then that's you have to potentially pay more attention to. So now we define this department, and then you have some extra attributes by reading this diagram, right? The extra attribute is that some of the employee is managing this department. Some of the employees like either director or manager of this department. So you have a new attribute, which is the manager's social security number, also the starting date. Starting date in this case we have, because this relationship type has attribute called the starting date. Maybe there's another attribute with ending date. Then you get an extra attribute here. Now the primary key is name. And the foreign key is that they subset. Now the manager's social security number is a subset of the social security numbers of the employment set. Right? So now there is a different set. So and this is a subset. Most likely it's a proper subset. How can we model the total participation? Right? So we can add like a not empty constraint to this manager SN for the total participation, meaning that this department has to always be managed by someone. Even the director maybe is on overseas, maybe there is some acting directors as well, right? Temporary ones as well. Just some constraints. In this case, we can do that when we created the table. Create the schema, I mean. Why don't we extend the relation schema of the partial side entity type? Why? So partial side, which is this side, right? This side, partial side. And then this is the total side, 999, total side, 19 is partial participation. So this may cause many empty values, if you think about it, right? And then we don't want to have too many empty values, and empty values are like kind of a waste when we do the create this relational schema. So the second method is the merge the relations. This is for the case where majorly we have the total participations on both sides. Right? How can we translate this one? Like, so this is total participation, total participation. So if participation on both sides is total, we may merge the relation schema of the both entity types and the attributes of relationship into one single relationship. Now connect, you basically connect the department and then the employment and the department. So this is like one relation schema. You can create it this way, right? Like then you combine all the attributes as one piece. Like so, all the OWASP here are putting together as one. So basically, you put everything together, right? Now the primary key. Going back to the primary key, you just always think about if this can uniquely identify this whole set. So in this case, we can take any social security number or the department number because this is a total participation. How can we model the total participation in this case? We can also add a not-null value constraints to both this SSA and the department name as well for the total participation. Meaning that this total participation here meaning what? Like each employee manages this department, and this department is always managed by an employee. That's the that's called the total participation, right? Total participation. So is merging them always a good solution? In this case, is it always a good solution? So something like you can think about it, right? Maybe if it's not a good solution, maybe you can define different schemas in this case, and then you, in that case, you have two schemas, and right now it's one schema, and then you can think about what's the difference, which one maybe save some storage or more friendly. So that depends on usually the scenario. In general, so merging of them is not always a good solution. So cases like this, like the two entity types represent different entities in the real world. Right, they are different, and if you combine them, and then you maybe have a good story, but they can be cases where we have the different type it's better to be managed. In other reasons is that the two entity types participate in different relation types as well. So maybe like in this entity, potentially there are other relationships, right? Like having separate relationship schema in this case leads to more efficient updates than a single relation schema. What I mean is that, like say, these ones may have other relationships, not just managers. And then this department have other information as well, other relationships as well. The department may be like, say, you have another relationship, like say, offer courses, courses should be like a rectangle entity. And then in that case, you want to do different schema to map these entities, which is more efficient. So usually based on a scenario. So the third method is the cross-reference one. So cross-reference one is for this partial participation. Partial participation. So if both sides are partial, we may create a new relation schema which cross-reference using the primary key of the relation schema and then combining with the foreign key. So now in this case, we build a relation schema for the managers, like this action, this relationship. And then the managers is coming from some employee, social security number, and then some department, meaning that some guy in the employee set, some tuple in this employee set and manages a department, right? So this is SSN, one SSN manages the department. What's the starting date, right? Because this is partial and it's not like total, so this is cross-reference. And then now this social security number, we have to obey the referential constraints, the foreign key. Social security number has to be a subset of the employee social security number. The department name has to be the department subset as well. Can we still merge them into a single relationship using previous approaches? So we cannot, because otherwise we would be, what would be the primary key, right? If you merge them, you cannot identify a primary key, right? Then that's meaning that you violate the, what's the constraints? There are 4 constraints. The key constraints, right? Violate the key constraints. If you have a schema, then you should have a primary key. In this case, you cannot identify a primary key. So that's step 3, 3 different approaches to build up the binary one-to-one relationship. Now for the binary one-to-n relationship type, this is pretty simple in the case that you always look into the n side. So you check those numbers. This is the n side. Then you just look into the n side to build a schema for this n side entity type. So build a student. So social security number, all the attributes has to be automatically there. And then add some uniqueness from the other entity. The uniqueness in this case is the department code or major department. In this case, you may change the attribute name a little bit. And then you have the primary key, foreign key. So here, now foreign key, the referential constraints making more sense, I hope, right? The constraints we talked about. Step 5, many-to-many relationship type. So for many-to-many, so create a relationship with the attributes, and then you look into that, create a record in this case, look into the middle one, the relationship type. So the social security number, section name, course name, this is to uniquely identify what's going on here in this many-to-many relationship. Always, maybe when you build these connections, always think, what are the options to make this thing to be unique, to not confuse the readers, to not confuse readers. Always think about if you can uniquely identify something, not confusing the logic there. So that's the key here, I think. Like always, like the primary key, foreign key. This is for the referential constraints. Step 6. This is for the case where we have the multivalued attributes, which is represented by the double circle or double aura. Like here, the addresses has a set of information like the country, the province, or the states, and other informations, right? So they have some many attributes, multivalued attributes. So in this case, for multi-valued attributes, what we do is that we create an entity for this. We do now I hope you don't get confused. When we try to create some relation schema, what are the pieces we want to create the tables? The pieces, number one is the entities. Number two is the relationship type, right? The diamonds. So your rectangles, you create a schema, usually. And then you have a diamond, you'll create another one. And then if you have a multivalued attribute, like this double circle, you create another schema. So those are major three pieces that you want to create. So usually, when you have a diagram, look into these pieces: rectangles, diamonds, and then the double circles. Sorry. So once you see a double circle, you just define a relation schema. So employee addresses like social security number and address. That gives the uniqueness in this case. And then the foreign constraints as well. And then the other steps, right? So the other steps, which is like the mapping, the n array types, and then the subclasses that we previously mentioned. So this is the how we generally convert from a diagram to a like a schema, set of schemas where we can actually using the SQL code to do the queries for the data. Now this is the kind of end of this class for this week. So I want to somehow recommend you to take a look at this paper. This is a very beautiful paper. The major kind of recommendation is in the sense that when you read it, you think away. You think that date back to that year, right? Or the 70s, you think about there's no such thing. And you are the first person to think about, to develop such a topic, such an area. Then what would you like to do? What's your strategy, right? And then consider a little bit like this way. So this is a very well written paper and very well established. So the first paper in SAM transactions and database systems. So this is actually a very famous journal. And then also the first international conferences on very large databases. And then like a little bit about Peter Chen. He has lots of awards, right? And also these days, because he kind of like opened a whole new area for data basis management, whole area. And then there are now awards named after him, right? The Peter Chen Award, and then particularly for the researchers towards the databases system. And then there's another one, the young scholars as well. So this is quite area where that developed like over the past 50 years or so. So I'll stop here. Next topic is the functional dependencies, and then Professor Qingyuan will take over. Next week, you will see Professor Chen here. And thank you very much for your support, and good luck with the rest of the semester. Thank you.